Hi, my name is Brooke, and I'm from the Washington State University Department of Chemistry, and I'm here to talk about the Chem102 buffers pre-lab. So we're going to start with question 1, which is asking for a description of how you're going to make your buffers in this lab. So what we're looking for is not just a regurgitation of what's in your procedure. We want to see a summary of what you're doing to make these buffers, so we really understand that you know how and what you're going to do in lab. So some of the things that you want to include is any important glassware. The marker doesn't feel like working today. That's okay, that's why we have spares. So, like I said, any important glassware. This would be your volumetric pipettes, anything that has any sort of readings that you're going to have to take, or anything just kind of special, like you use a condensator 1 week. And since this is a buffers lab, you also want to include any solutions you're using. Remembering to include the amount with units. And finally, you want to include any special techniques or equipment you're going to use. And again, we're just looking at your summary of procedures so we know that you are coming to lab prepared. So now for question 2, you're asked to consider 2 of the buffer solutions you will make in this lab. One of them has more sodium dihydrogen phosphate, and the other one has more sodium hydrogen phosphate. So what's going to be important for this question is understanding the Henderson-Hasselbalch equation, which is pH equals pKa plus the log of your concentration of your conjugate base over the concentration of your acid. Remember, in this equation, your A stands for your acid. So one of the things you need to consider is what, in this instance, is your conjugate acid, or your conjugate base, and what is your acid. For that, you need to remember what our definition of an acid and a base is. An acid is something that's going to donate protons to solution. And a conjugate base is something that's going to pull hydrogen ions out of solution. And remembering also that when you have a high pH or an increase in pH, that means that there are less hydrogen ions in solution. You have more of this conjugate base pulling these protons, pulling these hydrogen ions out of solution. If you have a lower pH, that means you have an increase in these hydrogen ions being deposited in solution. You have more H+. You have more of your acid in solution. So now when you're thinking about whether you have more of your NaH2PO4 or more of your Na2HPO4, right? Your dihydrogen phosphate, your hydrogen phosphate. You need to think about which one of those is going to give hydrogen ions and which one's going to take hydrogen ions, more likely to. So then for that, you need to look at this ratio, right? We need to figure out what's happening here that's going to cause a change in our pH. So that's when we need to look at our fraction, right? When you have a higher number on top, so you have a concentration of your conjugate base at 0.5, and your concentration for your acid is 0.2. When you have a bigger number in your numerator and a smaller number in your denominator, you're going to get a larger number, right? 2.5. Think about what this 2.5 is going to do to your overall pH. Versus if we had a conjugate base concentration of 0.2 over a concentration of 0.5 for your acid. That's going to give us 0.4. So we have a higher acid amount on the bottom. It gives us a smaller number. When we have more base, we get a larger number. So that's how you're going to figure out how to answer what the differences between these two solutions in pH is going to look like. All right, now we're going to talk about question 3, which is, you have a solution that contains hydrofluoric acid and sodium chloride. The pKa of your hydrofluoric acid equals 3.14. The pH of the overall solution, 3.21. First thing you should notice, that our pH is greater than our pKa. Going back to question 2, remember what a higher pH stands for, right? So then we go back to our Henderson-Hasselbalch equation. pH 3.21 equals pKa 3.14 plus log of our concentration of our conjugate base over our concentration of our acid. So if our overall pH is higher than our pKa, then we know that something had to happen with our concentrations for there to be a change in our pH. What you need to figure out for this question is how the concentration of our conjugate base and our conjugate acid can affect the overall pH. Going back to question 2, think about how when we had an increase in conjugate base versus an increase in our acid, how that changed the pH. Then think about how the concentration difference, what that would look like in solution. Would we have more protons, more hydrogen ions in solution? Would we have more conjugate base in solution? So that's what you need to be thinking about with our Henderson-Hasselbalch equation, and think about what a higher pH means to figure out the answer for this question. And now on to question 4. For question 4, we're looking at a quantity of carbonated water is added to 2 different solutions, but in this case I'm going to refer to it as 2 different beakers. So in the first beaker, beaker A, we just have water, just plain old H2O. And in beaker B, we have water plus our sodium dihydrogen phosphate in a 50-50 mix with our sodium hydrogen phosphate. So the question is, when we add carbonated water to both beaker A and beaker B, what is the pH difference going to be between the two? And what kind of magnitude of pH changes is the carbonated water going to have in beaker A and in beaker B? So first we need to look at CO2. What happens to CO2 when we put it in water? It's going to form something called carbonic acid, H2CO3. So this is our carbonated solution that we're putting in beaker A and beaker B. So then the other question is to ask, if this is carbonic acid, what is it going to do in our water solution? So, carbonic acid, H2CO3 in water, because both our beakers contain water. What is it going to make? It's going to form bicarbonate, HCO3 minus, plus protonated water. Another way to write this, H plus protons, hydrogen ions, and water. So the question is, if we have our carbonic acid solution put into beaker A and beaker B, is there going to be a pH change? So the question here is there something in those beakers that's going to change how much protons are in that solution? Is there something there that's going to suck up the protons or put more protons in solution? And if so, how much different is that pH going to be seen? How much more protons are you going to see in solution, or how many more protons are going to be taken out of solution in beaker A versus beaker B? And that's how you answer question 4. And that is this Buffers lab explained, and I hope that helped. Thank you.